Hello, dear students. I welcome you all on behalf of Sri Jayendra Ranzone classes. In the previous lectures of wave optics, we have seen the different theories of waves and nature of light, the Eugene's principle, Young's double-slit experiments, the interference patterns, conditions for dark and bright widths, dark and bright bands, the constructive and destructive interference, etc. Now, today we are going to see the polarization of light. First, let us understand what is the meaning of polarization. As we have considered light as an electromagnetic wave, if we take a point source of light, the light is transmitted in all the possible directions. As we can see here, light is transmitted in all the possible directions. Now, if we consider light to be an electromagnetic wave, if this is the direction of propagation, then we will have electric and magnetic field vibrations perpendicular to it. If this is electric field, then this is magnetic field. So if the vibrations are in all possible direction, propagation is in all possible direction, then regarding electric field's vibration is also possible in all the direction. But if we limit this vibration in particular direction only, let's say we have limited that the light wave having vibrations in vertical plane only can exist, then this kind of light is called polarized light. The natural or normal source of light is unpolarized light. So in unpolarized light, the vibrations are in all possible directions. And in polarized light, the vibrations are in particular direction only. There are multiple methods of getting the unpolarized light polarized. One is Malus effect by using polarizers. Another is by refraction. And the third one is by reflection. With these three methods, we can achieve polarized light. So let us see them one by one. First method, let us see polarization using polarizers. These polarizers are the natural crystals. They are quartz crystals. Their natural tendency is to let away the certain vibrations of light passing through them. It will block another light. So let's say this is the polarizer. This is the axis of polarization. If we incident the light ray to this polarizer, this incident light ray is unpolarized. So it has vibrations in all possible direction. But this polarizer will allow light which has vibration parallel to its axis. So outside of this polarizer, we will get only this much amount of light. So this output light is polarized light. If we want to shift it by certain angle, then we can use two polarizers. In this situation, one is called polarizer and another is called analyzer. We are using this two such that their axes are making certain angle theta with each other. This is the incident ray. This angle is theta. Only light having vibrations parallel to the polarizer will pass from it. Now, through analyzer, only light having vibrations parallel to its axis will pass through it. So we can see that intensity of light coming out of the polarizers and analyzers will decrease. So how much will be the intensity? That is given by the Malus law. The statement of Malus law is this way. If I naught be the intensity of the polarized light, incident on the analyzer, and theta be the angle between the transmission axis of polarizer and analyzer, then the intensity of the light transmitted through the analyzer is given by I is equals to I naught cos square theta. If A is the amplitude of light transmitted through the analyzer, and A naught is the amplitude of unpolarized light incident on it, then we can write A square is equals to A naught square cos square theta. So A will be written as A naught cos theta. Now, if I be the intensity of unpolarized light incident on the polarizer, intensity of light incident on polarizer and I is the intensity of light transmitted through analyzer. Then I is II by 2 into cos square theta and I is equals to I naught cos square theta. Comparing this two equation, we can write I naught as equals to II by 2. So only half intensity is transmitted through the polarizer. For the crossed polarizer and analyzer, theta is equal to 90 degree. If polarizer and analyzer in such a way, then theta is equals to 90 degree, then I is equals to I naught cos square 90, which is equal to 0. The polarization confirms the transverse nature of the light wave. Let us see some conceptual questions. Polarization confirms which nature of light wave? The answer is transverse. Which of the following methods can be used for polarization of light? Reflection, refraction, double refraction. All of these methods can be used for the polarization of light. Now, let us understand polarization of light by reflection and the Brewster's law. Let us say the unpolarized light is incident on air glass interface. The angle of incidence here is I. Light is reflected, some part of light is reflected and some part is refracted. If light is incident at particular angle, the reflected light is completely plane polarized in the plane of incidence. That means vibrations will be like this. At particular angle, the reflected light is completely plane polarized. This angle of incidence is called polarizing angle. So if light is incident at particular angle, the reflected light ray is completely plane polarized. This angle is called polarizing angle. At the angle of polarization, the reflected ray and refracted ray are mutually perpendicular. Here this is refracted ray, then these two are mutually perpendicular. The angle of incidence of ordinary light at which reflected light from transparent medium is completely plane polarized is called polarizing angle or the Brewster's angle. Or angle of polarization. Now let us prove the law, Brewster's law of polarization. We can apply Snell's law here. This is medium 1, medium 2. N is equals to sine IP divided by sine R. R is the angle of refraction. But R can be written as R plus R dash is equals to 90 degree. This total angle is 180 degree. If this much angle is 90, then R plus R dash can be written as 90 degree. So R can be written as 90 minus R dash. So N is equals to sine IP divided by sine of 90 minus R dash. So sine IP divided by cos R dash. IP is the angle of incidence and R dash is the angle of reflection. So we can write IP is equals to R dash. So we can write N is equals to sine IP divided by cos IP, which is equal to 10 IP. So polarizing angle IP is equal to 10 inverse of refractive index of medium. This is the Brewster's law. Let us see some question. According to Brewster's law, which one is correct? Third option is correct. Mu is equals to 10 IP. At polarizing angle, the angle between reflected and refracted ray is 90 degree. They should be mutually perpendicular. At polarizing angle, incident unpolarized light is reflected as which light? It is reflected as plane polarized light. Now, let us understand the Young's double slit experiment of diffraction. Here, there is a source of light from which light waves are coming. We have drawn wavefront. Each point on wavefront will behave as individual source. So they will have their own wavefronts. If the crests of wave intersect, then bright is created. And if crest and trough of waves are interfering, then dark band is created. We have kept a screen in front of the source, so we will get dark and bright patterns. Here at the center, bright band is created, that is taken as 0. Above that there will be dark band, above and below, and successively dark and bright bands will occur. Let us understand the arrangement for the interference pattern. We used an ingenious technique to lock the phases of the waves emanating from S1 and S2. He made two pinholes S1 and S2 very close to each other on the opaque screen. These were illuminated by another pinhole that was in turn lit by the light source. This is single pinhole lit by the light source, and these are two slits S1 and S2. Light waves spread out from S and fall on both S1 and S2. That we can see in the figure. The front view of this arrangement can be seen in figure B. Here, S1 and S2 behave like two coherent sources because light waves coming out from S1 and S2 are derived from the same original source. So they will have same frequency, same amplitude, and the phase difference, and there will be just a phase difference between them. Thus, the two sources S1 and S2 will be locked in phase. They will be coherent like two vibrating needles in a water wave. The spherical waves emanating from S1 and S2 will produce interference fringes on the screen G dash. The position of maximum and minimum intensities can be calculated by using the analysis given that for an arbitrary point P on line G dash corresponds to maximum. So let us assume that at point P, the maxima occurs. Meaning of maxima is that intensity is maximum. The position of this point P from O is X. Now, to obtain the maxima, condition for maximum intensity is that the path difference between the two light waves approaching at point P should be multiple of lambda. So, the path difference S2P minus S1P should be multiple of lambda, where n is equals to 0, 1, 2, and so on. This is equation 1. Now, from the figure, we can write S2P square minus S1P square is equal to, using the Pythagoras theorem, we can write d square plus x plus d by 2 whole square. This much distance is d, and this distance is x minus x1p. Minus d square plus x minus d by 2 whole square. Simplifying this, we will get 2xd. So, S2p minus S1p can be written as 2xd divided by S2p plus S1p. Here we have written S2p whole square minus S1p whole square as S2p minus S1p into S2p plus S1p. This is equation 2. Now, if x and d are very less than capital D, that means screen is kept far away, then negligible error will introduced if S2p and S1p is replaced by 2D. So we can write S2p plus S1P is approximately equal to 2D. So we can write S2P plus S1P is equals to 2D in the equation. We will get S2P minus S1P is equals to XD upon capital D. Hence, we will have constructive interference resulting in a bright region when X is equals to Xn is equal to n lambda d upon small d, where n is equal to 0, plus or minus 1, plus or minus 2, and so on. For this condition, we will have constructive interference. Now, on the other hand, we will have a dark region near X is equal to Xn, that is n plus 1 by 2 into lambda d by small d, where n is equals to 0, plus or minus 1, plus or minus 2, and so on. The dark bright bands appear on the screen. Such bands are called fringes. When small d is when capital D is very greater than small d and white light source is used, then wavelength absent in front of the sources will be d square by capital D, d square by 3d, d square by 5d. This wavelength will be absent when white light is used. The path difference is given by d square plus small d square is equals to d square by 2d of the point. And the path difference for dark fringes will be d square by 2d, that is equal to 2n minus 1 lambda by 2. For dark fringe, condition is the path difference must be odd multiple of lambda by 2. The distance between two consecutive bright and dark fringes is called the fringe width. So fringe width beta is given by xn plus 1 minus xn. Simplifying it by putting the value, we will get beta is equals to lambda capital D by small d. So the bright fringes are created due to constructive interference and dark fringes are created due to destructive interference. Let us see some conceptual questions. In Young's double slit experiment, sodium vapor lamp is replaced by neon lamp. Then what will happen to the fringe width? Here, as the wavelength decreases, the fringe width will also decrease. Beta is also decreased. Next, a fringe is a locus of constant amplitude, constant intensity, constant phase, and same wavelength. Fringe is a locus of constant phase. Young's experiment established that light consists of waves, light consists of photons, light consists of corpuscles, and light has dual nature. Here we are using, for Young's experiment, Eugene's wave theory, because we are proving it by interference of waves. So it establishes that light consists of waves. This is all for today. Thank you.